All right, let's dive right in. Today, we're going to look way past the 3D printers you might have seen and into a future where we don't just print objects, we print fully functional, responsive systems. We're talking about pushing printing technology all the way to 6D. For years, we've all heard that 3D printing is the future of how we make things. And don't get me wrong, it's absolutely revolutionary. But what if I told you that 3D is just the beginning? It's just the starting line. We're already moving into dimensions that sound like they're straight out of science fiction, but are very quickly becoming science fact. First up, let's talk about 4D printing. So, what's the fourth dimension here? It's time. Yeah, you heard me right. These aren't static objects. They're actually programmed to transform themselves after they've been printed. So imagine a medical stent that unfolds itself once it's inside your body, or a solar panel that automatically tilts to follow the sun. That's 4D. Then we have 5D printing, and this one is all about pure mechanical strength. Instead of just stacking flat layers one on top of another, a 5-axis printer can actually rotate and move, printing along curved surfaces. Now, this might sound like a small change, but it creates objects that are dramatically stronger. We're talking 3 to 4 times stronger and way more efficient, because the layers actually follow the object's natural shape. And this brings us to the main event, 6D printing. It's the ultimate combination. You take the multi-axis, super strong approach of 5D printing, and you merge it with the smart, responsive materials of 4D printing, and what you get are objects that are not only incredibly tough and efficient, but can also change, adapt, and react to the world around them. This is the new frontier. But how is any of this even possible? Well, the secret ingredient, the key that really unlocks this whole revolution, is the ultra-fast laser. To build these incredibly complex, responsive, and often microscopic structures, you need a tool with a level of precision that's almost hard to imagine. Okay, so here's the key difference. A conventional laser is kind of like a hot knife through butter. It works, but it melts the material, which is messy and pretty imprecise. An ultra-fast laser, on the other hand, fires in femtoseconds. That's a quadrillionth of a second. It's not a hot knife. It's like a scalpel made of pure light. It doesn't melt the material, it instantly vaporizes it with almost zero collateral damage. The physics here is just fascinating. These laser pulses are so ridiculously fast, they hit the material and transfer all their energy before the surrounding atoms even realize what's happened. Seriously, there's no time for heat to spread. The energy goes in, the material just vanishes, and the edges are left perfectly clean. That is the secret to getting precision on a nanoscale. So what does that kind of precision actually look like? It's one thing to talk about it, but it's a whole other thing to see what this scalpel of light can really create. The results are genuinely mind-bending. This right here is the iconic microball. To give you some sense of scale, a single red blood cell would look absolutely enormous next to this thing. We're looking at manufacturing with a level of detail that was pure science fiction just a few years ago, all built layer by tiny layer with an ultra-fast laser. And this shot demonstrates the laser's power perfectly. Printing with pure copper is incredibly difficult for normal lasers. Why? Because copper is so good at conducting heat that it basically sucks the laser's energy away faster than it can melt, leaving you with a porous, weak structure. But an ultra-fast laser dumps its energy so quickly, the copper has no time to conduct it away. You can see right here how layer by layer it can build a dense, solid copper object. And it's not just about simple shapes either. Look at this freestanding gold helix. It's a complex, self-supporting 3-dimensional structure built with microscopic precision. This shows the ability to construct these really intricate architectures from the ground up on a scale that's almost impossible to even comprehend. Now, all of this leads to a very logical question. If you're focusing a beam of light to a tiny spot, how can you possibly create a feature that is even smaller than that spot of light? It seems like it should defy physics, but there is a very, very clever trick at play here. So how's it done? The magic is a technique called two-photon polymerization. Think of it like this. Instead of needing one big photon of light to trigger a reaction, this process needs 2 smaller photons to arrive at the exact same spot at the exact same time. And that's only likely to happen right at the super intense center of the laser beam. So even though the laser beam itself has a certain width, the reaction only occurs in a tiny pinpoint right at its heart, which gives us this incredible subdiffraction resolution. The formal name for this technique is multiphoton lithography, or MPL. And by using this clever two-photon trick, we can effectively bypass the normal physical limits of light. It's really the foundational technology that allows us to build things like that microbowl with such mind-bending detail. Okay, so we've established we can make incredibly small things with unbelievable precision. But 6D printing isn't just about making small forms. It's about printing function, and that function starts right at the surface. This is where it all starts to come together. What if the material itself wasn't the only thing that mattered? What if you could fundamentally change how that material behaves, whether it repels water, whether bacteria can grow on it, whether it's slippery, just by carving a microscopic pattern onto its surface? Well, this is achieved with something called LIPS, that's laser-induced periodic surface structures. Using these ultra-fast lasers, we can etch microscopic ripple patterns onto a material. These textures are so small they're on the scale of a wavelength of light, and they are not for looks. They're engineered to give the surface an entirely new properties. And the applications here are incredible. You can create a surface that's so water-repellent it cleans itself, just like a lotus leaf. You can texture a medical implant to encourage your own bone cells to grow onto it, or to prevent bacteria from ever getting a foothold. You can reduce friction on tiny moving parts, or even change the color of a metal without any paint, just by altering how it reflects light. You're literally printing function directly onto the material. So now let's put all of these pieces together. We have the ability to print complex shapes, we have the precision to work at the nanoscale, and we have the technique to embed function directly onto surfaces. This is the path from making simple static objects to printing integrated dynamic systems. So you can see the whole evolution. We started with making basic shapes, then ultrafast lasers let us make detailed microshapes. After that, LIPS allowed us to print function. The 6D goal is to merge all of this into a single process, printing an object that has its shape, its microfeatures, and its function, all built in from the very start. And this isn't just some theoretical exercise. Think about the possibilities. Truly customized medical implants, printed with textures that ensure perfect integration with the body. Aerospace parts that can subtly change their own shape to optimize airflow. Building materials that can heal their own cracks. Or even drug delivery capsules that only release their contents when they receive a specific signal inside your body. And underpinning all of this is a massive leap in structural integrity. By printing along those curved, optimized paths instead of just flat layers, these functional objects aren't just smarter, they're fundamentally stronger. We're talking about a 3- to 4-fold increase in strength while using less material. It's a complete game changer. And this brings us to our final thought. As we move into this future of 6D manufacturing, the lines we're used to drawing, they start to blur. When an object's material has computation, reaction, and function woven directly into its very structure, it raises a fascinating question. Where does the material end, and where does the device actually begin?